I was going to make a quick video to motivate the three big examples that we're going to have in class. Probably had classes that have a big question or a big central idea that you're going to explore over a series of units. The big central question that we're going to ask in every single class that we go through in the machine learning class is simply, how does it work? How does this model actually produce the behavior that we see? And so I find it more useful to have examples of domains that we're going to work in. And there are three big ones that we're going to return to over the course of the class. These will be sort of the organizing pieces of knowledge. So you should understand these domains, these topics, these ideas, and we're going to dig into and figure out every single piece of how they work. Hopefully, by the end of the class, you will be able to kind of reason through, even if you don't know exactly every model, exactly every parameter, exactly every optimization, you'll be able to reason through kind of how you would go about doing these pretty spectacular machine learning examples. You'll also learn the foundational knowledge that will support all these and some different models as well. But these will be things that we'll reference all the time. So for my three big examples, I have picked first Kaggle. Kaggle is something that probably a lot of you know about. It is a data science bounty board. You can find it online and you can find a list of challenges that they have, sometimes with reward purses. Kaggle is not as popular as it once was. Companies have basically learned to hire internal data scientists and don't put their data out on the web for just anybody to sample and use and get money from. But there are still some bounty boards out here. You can still try your hand at winning $50,000 or so by training a data science model. The classic ones were much higher about 5 years ago. There's lots of stuff in the kind of the $1 million range, but pretty much none of that left anymore. The thing that I think Kaggle is really useful for is it sets up this very basic idea. I'm going to give you some data. I want to know something about the data. Like I want to, for instance, this is the passenger screening algorithm. I'm going to give you some pictures of bags going through an X-ray scanner. I want you to tell me if the bag is dangerous, if I should check that bag or not. Deepfake detection. I'm going to give you some pictures, some of which are real, some of which have been deepfaked. I want you to tell me which ones are the deepfakes. Build me a classifier, sort these into piles. Patients who are admitted to the hospital, right? Just looking at their historical data, looking at the numerical data of, their past treatment, maybe physician's notes, text data, things like that. Tell me which ones are going to get better. Tell me which ones might be readmitted. Tell me which ones might have a secret health condition. And of course, then, something very simple like, hey, I gave you some house prices. Can you tell me whether they're going to go up and down in the next 6 years? How much is this house going to sell for in 6 months? How much is this house going to sell for in a year? Zillow, incidentally, totally made their money back on this. They put out the reward for $1.2 million. They got a pretty good model that estimated the price over time. And then Zillow actually went out and with their own money, bought all those houses and bought all the ones that were slated to go up in value and sold them off. And they probably made their money back on, 3 sales, something like that, 3 home sales. And they did tens of thousands. So it worked out pretty good for them. So this is your basic machine learning framework. I'm going to give you some data. I want to know some answer. Set up a model in between. Incidentally, this will be a great platform for us to talk about different kinds of measures, to talk about things like false positives. If a patient comes in and we say that they're going to be readmitted, but then they are not, right? How often does that happen? Or false negatives. The deep fake is so good that it gets bias, right? That's a thing we can talk about, the different measures we can talk about. It will give us a chance to talk about things like classification versus regression, do things about exploring the data, about different kinds of data ingestion and things like that. And I think that this is kind of the plain vanilla framework of machine learning where, you have data, you want an answer. What are the algorithms that get you from point A to point B? Incidentally, one of the algorithms I like to bring up a lot that we will talk about is what I kind of call the Kaggle crusher. One of the reasons that Kaggle is not as popular as it once was is there are frameworks like the autoencoder with the XGBoost that are just very, very effective at doing the proper classification. And once these pipelines were kind of understood and pre-built and some of these notebooks made, they would just be dropped on the problem over and over and over again and win most of the competitions running away. And people who are actually able to perform the best, it ceased to be so much about having a good model and became more about finding clever ways to cheat. So this model, therefore, is actually a really nice general purpose one that we'll talk a lot about in the class. You'll learn how to build one of these by the end of the semester. The second interesting machine learning case, which kind of stands in for all of our computer vision, is this implementation, which you may know of by the name like Deep Dream, or this specific implementation is called QGAN plus CLIP, which is a variational autoencoder with a contrastive language model on the front end that helps, identify the pictures that are going to be used as seeds to generate the model. There are a large number of networks that are actually embedded in this, and they all kind of work together to produce these cool, trippy figures. You may have heard of more recent versions of this, like DALL-E, that came out of OpenAI last year, that use several more constraints in order to get more realistic seeming images, in order to produce images that are in specific art styles or actually pretty photorealistic. And those are pretty cool as well, build on very similar technology to what this has, just kind of with more training, with more data, and with more engineering put into the architectures. The major insight, I think, for the second example is to understand that images are just another form of statistical data. From the perspective of the models that we are working with, images are not special. Because we're primates with elaborate visual systems, we look at pictures and we don't think of them as ones and zeros. But to the computer, hey, it's all just numbers. Each one of those pixels is just a value, right? There is a big array of pixels, that big list of pixels, each one with a number in it. And you can train a model to classify different pictures according to that single numerical vector. You can figure out, you can try to learn the parameters of a distribution of images. So all of the images that contain cats, you get a big list of images that contain cats, and that constitutes a statistical distribution. Every single one of those images is just a long list of pixels. Every single one of those long lists of pixels has some number in it. And you're trying to learn the parameters of a distribution that characterizes, say, the cat distribution of images versus the dog distribution of images. Very straightforward image processing sort of stuff. We will start very basic. We'll start with those simple things like a perceptron, simple things like the MNIST digits, which are a very famous kind of data set that you use over and over again in machine learning. They're handwritten digits, and they're actually the basis of a perceptron that was trained to read zip codes on mail. But we'll build up from that toward these more complex entities like variational autoencoders that we will then using this kind of and convolutional nets and a lot of the kind of neural network based image stuff. Right. And my third example, and actually one of my favorites because it's a colleague of mine at the University of Illinois that I worked with in the language acquisition group. This is BERT. So BERT is a little robot who you can teach things like learning to wave. Okay, he's explaining to BERT how to, that this is up, this is left, this is down, this is right. And now he says, put your hand to the right. Oh, hey, he gives him instructions like up, down, left, right. And lo and behold, up. He moves his arm as if in that area. Okay, so there's a lot going on here. There's a robotic system, obviously, that's pretty spectacular and the thing that gets a lot of attention. But what's much more interesting is what's going on inside. So this is a language opposition model. It's actually a hidden Markov model. It has a series of states that the robot has learned to identify and is moving through. It has a linguistic model where it actually is hearing and processing the sound data that is coming in from the researcher. It is learning what those words mean. It is associating them with different positions in its motor system. And it's this beautifully sort of integrated system that uses a lot of different machine learning techniques, a lot of techniques from natural language processing, a lot of techniques from statistics and neural networks are all kind of going on in here. So it's a really cool example that integrates a lot of different stuff. So these are going to be our 3 examples for the semester. You will learn many other specific cases, but what I'm trying to do by framing the class around these 3 big ideas are get you to start thinking about how these things work, right? These are not black boxes. These are not difficult to understand. These are, machines that have some mathematics and some statistics behind them. But every single one of these examples here is something that you could build, you could put together yourself out of bits and pieces of code. Almost all of these are using the libraries for these are widely available, and you can easily pull a notebook and try them out. But what's more, all of the mathematics that undergird them, the statistics and the knowledge that are necessary to understand how these machine learning algorithms work are all, fairly publicly available and fairly straightforward. So every single one of these pieces, these spectacular technologies, either for making millions by classifying bags as dangerous or homes as valuable, generating weird trippy pictures of cyborg dragons, or talking to a little robot that will then do what you tell it. All of these things are actually well within the scope of what we will learn in this class. I'm not saying by the end of this class, you'll be able to build one of these robots. This robot actually costs about $8 million to build, but you'll have a lot of the skills you would need to understand what the software it's running does. And so think of these examples, commit these examples to memory. I will refer to them again and again. And my central question over and over again will be, how does this work? How does this work? How does this work? What is going on inside this machine learning model? So I will meet you in the next video where we'll talk a little bit about the class outline, and I will refer to these 3 examples as I go through that syllabus by saying, here's one of the models that we'll get that will contribute to our understanding of how cognitive competitions are won. See you then.